Okay, welcome to our webinar event. I am Ken Clairbout, K4ZW, president of the Potomac Valley Radio Club. And along with a great presentation tonight from Dean Straw and 6BV, this presentation is a little unique in that it's a collaborative effort this time between PVRC and the Northern Cal Contest Club, and we're delighted to be working with the guys out west on this. And what I want to do is I want to turn it over to Dean Wood, N6 Delta Echo, just to say a couple of words, and then he will pass it off to our presenter, and we'll go ahead and get started. So Dean, if you want to pick it up.
Great, thanks Ken. This is Dean and November 6 Delta Echo. Ken, I just want to thank you and the PVRC for hosting this webinar tonight, and I really applaud the great job that you guys have done over the last months on webinars. Terrific job. Well, I think the first thing we want to mention for just a minute is why are we having a collaborative PVRC and NCCC webinar tonight? You guys are already aware of the great PVRC webinars in the past and in the future. But you may not be aware that the Northern California Contest Club has also had its own webinar system and has hosted several webinars on various different topics this year. Those webinars are available for downloading. And actually, tonight's webinar was planned to happen on the Northern California Contest Club system. But after communication with K4ZW over the last number of months about ways that our two clubs could work together on webinars, and also with N6BV already having done a webinar on PVRC system, we wanted to give this a try for the first time tonight as a collaborative effort between our two clubs. And after the webinar, maybe tonight or tomorrow, at least I'd really be interested in your feedback about how this went tonight, how this worked for you, and if you would like to see our clubs collaborate more in the future on other webinars. So with that, I am pleased to introduce Dean Straw, November 6 Bravo Victor, as tonight's presenter. The topic is hints and kinks for using HFTA, but it's a lot more than that. Dean has, of course, been a senior assistant technical editor for the ARRL for 16 years. In the past, he's been editor of a bunch of different stuff, the ARRL Antenna Book, the ARRL Antenna Compendium, ON4UN Low Band DXing, K1VR's Antenna Zoning, ARRL Handbook a number of times, and co-authored a book called Simple and Fun Antennas for Hams. EE degree from Yale, 25 years of experience in the marine electronics industry. We know him best as the past president of the Northern California Contest Club and as a guru of antennas, transmission lines, and HF propagation. We also know him well as putting up huge scores from the N6RO Superstation. So with that, before I turn it over to Dean and 6BV, we just want to discuss a little bit about the format that you guys can expect tonight. Dean might cover this in a second, but what we're going to go through is a full demo from start to finish of the whole terrain gathering and analysis with W6YI. And then at the end of that whole demo and hints and kinks that Dean is going to talk about, Ken and Dean and 6BV will go through Q&A. So we're going to hold off on the Q&A until the very end because there's a really nice flow to the whole demo. Feel free to type in your question on that interface on the right that Ken mentioned a little earlier. Type it in. We'll get right to it at the conclusion of the demo. The other way you can participate is, of course, raise your hand like you did before we even started tonight, and then Ken will turn it over to you, and we can hear you ask a question. That's all I had. With that, I'm going to turn it right over to Dean Straw, November 6 Bravo Victor. Take it away, Dean.
Okay, thank you, Dean. N6DE Dean. This is Dean Straw, N6BV. And let me see if I can get control of this thing here. Hold on just a second. Okay, what I'm talking about tonight is a further explanation of what went on back in August 5th when I did the first webinar with PVRC. And that webinar on August 5th was entitled HF Antennas, DX or Domestic, What's Your Pleasure? And the focus there was on the necessary elevation angles to achieve area coverage as exemplified by a bunch of area coverage charts generated by VOA area. So it was elevation angles and area coverage. And tonight what I'm going to be talking about is more of the specifics of using the HFTA, that's the High Frequency Terrain Assessment Program, to get into the details on how to use that. I briefly introduced the HFTA program in August 5th, but now I'm going to go into much more details. All right. What I intend to do tonight is the outline of this presentation is I will briefly describe HFTA and then demonstrate how to get terrain profile data from 3 sources on the web. Arguably, getting the data to use in HFTA, the terrain data, is the most difficult part of actually using the program, and I want to show that it's really not all that difficult. There's ways of doing it that will be discussed in great detail tonight. And then after showing how to get the data, we'll describe some hints and kinks. I'm not sure if some of the European folks who are listening in, I guess we've got about half a dozen Europeans in attendance tonight, or rather very early in the morning for them. I'm not sure if they understand what the term hints and kinks is. What it is just secret tricks on how to use HFTA. All right. So to briefly, let me describe what the HFTA program. It's the letters HFTA stand for High Frequency Terrain Assessment, and it is a full Windows program. It started off in the DOS world about 15 years ago as a Fortran, a compiled Fortran program that it's much easier to use in the present implementation, which is a Windows program. I hear noise in the background, Ken. Is there somebody who's got a microphone that's open?
I'm not hearing it, but what I can do is I will mute the rest of the, actually mine was muted, so I'll mute the rest of the staff except for yours.
Okay, that's good. Thank you. All right, so what HFTA does is it's a ray tracing program, and it traces the path of rays over two-dimensional terrain. And what it takes into account as it's doing its computations are reflections and diffractions. Of the two, diffractions are considerably more difficult to do than simple reflections. The display of elevation angles that was discussed in great detail in the August 5th webinar, the display of those elevation angles that are needed to achieve area coverage are integrated into HFTA. HFTA is bundled on the CD-ROM that accompanies the 21st or the 20th editions of the ARRL antenna book, for which I was the editor for the last 5 editions. I have a great deal of fondness for that book, by the way. Okay, now, like any software developer, I'm going to plead that whoever uses the software, please read the manual. The manual is a PDF called HFTA.pdf, and it's automatically brought up when you click on the Help button up in the upper right-hand corner of the program. Let me just show you that. I'm going to bring up HFTA and click the Help button. And if everything is working right here. By the way, this is a very risky demonstration tonight. It's very risky in that I will be using a lot of web sites and if any of them is down or if any of them are particularly slow, it could be a disaster in the making. So what I'm going to do is I'm going to cover my bases here. I'm going to have non-live demonstration set of slides to illustrate what the live portion of each point that I want to cover, so that you can see a quick rundown of what buttons I'm going to be pressing, and then hopefully during the actual live demonstrations you'll see it actually go as it occurs. Okay, what you would do on this is you'd select the bookmarks, which gives you the table of contents. And for example, if you want to go to Appendix A, preparing a terrain data file, you just click here and it comes up. There are a number of, let's see, okay, there's, for example, if you want to access various databases that are described in here, you can click on various active URLs that are embedded in the document. Okay, let me shut this down and go back to the PowerPoint slideshow. All right, so please read the manual. Won't dwell on that anymore. Now, getting terrain data for HFTA, as I said before, arguably getting the terrain data itself, the topographic data, is the first and possibly the most difficult task in using HFTA. In this demonstration, what I'll be doing is showing that it really isn't that difficult to do. But what I've got to do is introduce you first to the microdem mapping program. Now, the microdem is a very comprehensive mapping program written by a professor at the U.S. Naval Academy by the name of Dr. Peter Guth. Dr. Guth is an amazing guy. He seems to be awake all 24 hours of the day, because whenever I've had any correspondence with him, he immediately gets back, even if it's 2 in the morning. Very talented programming guy and just an amazing guy. Anyway, he uses his program microdem uses digital mapping data available from the internet to create various terrain profiles. And after microdem generates the terrain profiles, HFTA then uses those profiles to do its analysis. Now, here's an example of a screen from microdem. This happens to be an example showing Anchorage, Alaska. And not only does it show the terrain in Anchorage, but it shows, I've also overlaid the streets, and you can see in the Anchorage airport over here. It's an extremely comprehensive program, microdem is. And I've adopted it as the main platform for getting data into HFTA. Okay, so getting data for microdem. Actually, for HFTA, the first way you can do it is do it manually by taking a look at a typical 7.5-minute quad, so-called quad USGS topo map, and perhaps putting a point where you're located and then stroking off an angle of let's say 45 degrees on the way from, in this case, Windham, New Hampshire, my old QTH back east, towards Europe, and then measuring using calipers and a ruler, measuring the distance from the tower base, and the break at each terrain break. You then enter into a disk file the elevation, elevation height, the altitude, that is, and it's a painful process. You can get about 1 stroke off at a desired azimuth angle. You can do it in about half an hour if you're real good, but more typically it takes you about an hour to do it. It's very painful to do it manually. Now then there is the so-called seamless USGS National Elevation Data Set, the NED files. They are easy to use, although the USGS keeps playing with the server site, and the server can be flaky at times, and that's why I've hedged my bets when I'm doing a live demo using NED. There's a third type of data available on the web for the U.S. By the way, this is for the U.S., the USGS, U.S. Geological Survey. Produces both the seamless data and the so-called DEM, the digital elevation model data. The trouble with the digital elevation model data is that the maps are the digital equivalent of the 7.5-minute quads, and these topographic files may, depending on where your location is, may require the merging of several or as many as 4 of the maps in order to cover the required areas. So merging can be kind of a pain in the neck. The latest data that's just become available in the last year, it's been released to the public, is the so-called SRTM, which stands for Shuttle Radar Topography Mission. space shuttle data done back about the year 2000 with radar. This has been released for use outside the United States, and I know some of our European friends are most interested in using that data. The resolution, by the way, is less than that available for both the NED and the DEM files because there's all kinds of issues. The U.S. government has issues, of course, about copyrights with other countries. For example, the British Admiralty is real stiff on copyright limitations for using their data, and also presumably they don't want super accuracy for places outside the U.S. that would complain about super accurate data. Okay, so I started out by saying I need a volunteer and needed the street address in the county, and I wanted a location where the towers should be on a hill, although not necessarily at the top of a hill. And I wanted only paved streets, no dirt roads, no RFD, rural addresses, no post office boxes. And actually got a little mini pileup of volunteers, and as he does in the RF world, Jim, W6YI's signal rose above the rest of the signals calling, and so I chose Jim's as being my volunteer for doing a demonstration for using his data. Thank you, Jim, very much, by the way. All right. So this, as I say, will be the dry run, so to speak, using just slides to demonstrate what I want to do. What I want to do is, first of all, use Google Earth to locate the location, the latitude and longitude of the base of the tower, or towers in the case of W6YI. However, you can also get the latitude and longitude of your tower or towers by using a GPS, a handheld GPS at the tower base, and getting the actual latitude longitude. One of the neat things about Google Earth, and I'm sure a lot of you are familiar with Google Earth, is you can type in an address. In this case, 32 Beacon Hill Road, Windham, New Hampshire, was my old location back east in New Hampshire. About 10 years ago when I used to live back east on the East Coast. And what will happen is once you type in the address, it'll zoom in, and you can zoom in down to, depending on the photography sources that they have, you can see, for example, what I've done is I've outlined where I had cleared out a bunch of forest with a chainsaw, and that was where my tower was located. And so what you do is you take the latitude and longitude down here at the bottom, and you write that down, and then you know what your latitude and longitude of your tower is, and then we'll use that data. Okay, let's go live now. What I'm going to do is, let's see. First of all, I'm going to do a QRZ.com search on W6YI. It's actually, I had done that. This is James K. Stevenson at 10250 Paso de Flora, Escondido, California. That is, we take a look at more detail, we can see that he is located in the U.S. county of San Diego. So let's do this. We're going to highlight his address and zip code. Control C copies it to the clipboard, and then we're going to open up Google Earth. Oh, I'm getting ahead of myself here a second. Just let me put his address in here. Shift, insert, enter. What it will do, what Google Earth will do is, I had already was spying on his location, but it will start way out here and then zoom in. This is Google Earth at work here, and what it shows is that the entrance to his area, I believe this is Jim's house right over here. In fact, can you unmute Jim W6YI's microphone now? We can converse during that.
Yep, Jim, you should be able to go ahead and speak to Dean.
Yes, Ken, that is the house.
Okay, good. And as we zoom in further, we're going to notice some things. Notice how the shadows are from his house are coming like this direction over here. That means the sun is back here. Well, if we look for towers, there's something interesting going on right here, especially when you see the shadow of it. That's your 140-foot tower. Is that right, Jim?
Yes, that is Dean.
Okay, and you had earlier given me the coordinates of it, but you can see that the coordinates are 30, down at the bottom is 3316.574 minutes north and 117 degrees 6.942 minutes west. And you use a slightly different nomenclature. You use the decimal degrees in your Google, but you took this data from your tower locations from Google. Is that right, Jim?
Yes, I did, Dean.
Okay, well, if you take a look over here, there's something interesting going on here. In fact, it kind of looks like a 40-meter beam, and it is indeed your second tower. If I recall correctly, that's where the location of your second tower is. You take another look over here, there's another interesting shadow, a tall, slim shadow in the right direction, which would indicate that at the base of it, right here, there's another tower, which is your third tower. Is that right, Jim?
That's correct. That's the 95-foot Sky Needle.
That's the 95-foot Sky Needle. This is 140 feet. This is, what is that about?
70-foot LM470.
Okay, and you've got a 4-element KLM at 70 feet, as I understand. And there's another antenna over here that you can just barely see, which is your fourth tower, and that is located at 3316.567 degrees north and 117 degrees 6.882 minutes west. Now let's do something here. Now that we've got your towers shown. Oh, by the way, if you do right-click on this and then look at the properties, you can see that's the latitude and longitude of that particular tower. All right, now let's use Google Earth to do something interesting. We're going to tilt Google Earth and then look around to see what the topography around Jim's location looks like. And you can see that the big tower is kind of down a slope here, since the primary direction that you're probably interested in is three directions. One, about 65 degrees to get towards the U.S., maybe about 35, maybe 30 degrees to get to Europe, and let's say about 305 degrees to get to Japan. Are those the most interesting azimuths, Jim, for you?
You're absolutely right, Dean.
Okay, and then, of course, there's going south about 110 degrees to get to South America. So what this is saying is that there's a small challenge, because there's a small hill on the way to both Europe and the U.S. And as we go into the use of HFTA, you'll see what the challenge actually involves. Okay, let's see. Let's get back. Okay, so what we've done is we found, and I've written down these locations on a piece of paper for Jim's tower location. Now what we're going to do is use the Seamless database to actually get that data. Now this is the URL that's needed. It's a USGS government website, Seamless, very straightforward. Again, the instruction manual for HFTA will give you a clickable link to go to this site. Now this is again, I'm going to do this passive non-live demonstration to show you the steps necessary. What you'll do is, this is the Seamless data site, and what you want to do is select this icon right over here, which is called the coordinates icon. And what we will do is we'll take the latitude and longitude of the tower, and we'll add and subtract 5 seconds of latitude, 5 seconds of longitude, and put it in, so to speak, into a box here. In this case, and by the way, I'm not going to even worry about the decimal the values after the decimal point. What I'm going to do is look at 42 degrees plus 5 at 55 degrees, minus 5 at 45 degrees, minutes north, and 71 degrees, 18 minus 5, 13 in other words, and 18 plus 5, 23 minutes of west longitude, and enter those numbers. Then going to modify the data request in the NED and choose the National Elevation Data Set, the NED data at 1 arc second, and choose in the drop-down box of the GeoTIFF format. Save the changes, return to summary, press OK, and then save the file that the NED database comes up with. Save that file to a known location. It's a good idea, by the way, to write down the file name because you can see that it is NED_09200234.zip, which makes a great deal of intuitive sense. Write down the number just in case. All right, so then what we do is open the zip file and extract the TIFF, the TIF data, which, as you can see, is in this case is a 1.444755 bytes in size. It's a fairly decent sized file. You do that using the Microsoft Explorer or WinZip, or one of those programs that can extract data from a zip file. Save it in a place where you can retrieve it. Save the map itself as a microdem file, perhaps labeling in this particular case n6bv-ned.dem. Then you close the file, reopen it. Okay, now we're going to go live and see if we can manage to pull this off here. So let's see, just a second. Okay, we're going to go to the National Seamless Database. Here's the define download area by coordinates. Push that. Now, what I'm going to do is choose Jim's tower number 1 as 33 degrees, tab over. It's 16.5732 minutes, but I'm going to just look at the 16 minus 5 or 11. 33 degrees, tab over, 21 degrees. Longitude 117, tab. 6.97, I'm going to subtract 5 from the 6 to get 1. Go to the other side, 117, 11. Okay, so now we've defined a box of data that I want to add area. Oops. This is where you want to watch out. Let's see. Let me go back. Just a second. What did I do wrong here? Clear the fields. 33, 16. That's 11. 33. 21. 117, tab over. 6 minus 5 is 1. 117, 11, add area. Okay, now I typed in the right numbers and it worked. Now, as a reference, the size that you take when you do this, plus or minus 5 minutes of latitude and longitude, is you'll get about a 2 megabyte size to download. But we've got to modify the data request, and we've got to select that GeoTIFF. It's normally default is ArcGrid. GeoTIFF. We go down to the bottom of this. Second, it's acting kind of slow. The database is save changes and return. Now we're going to download this data. And now this is where it can take as much as a couple minutes, in fact, to to come up so it's savable. Jim, you've done an HFTA analysis on your location, haven't you, before?
Yes, Dean.
Did you use the DEM data or the NED data?
Well, I used the DEM.
Okay, yeah.
And we did have all the information, if you recall.
All right, so it says save this. Well, when I press OK, it will save it. In this case, it will save it to my temporary subdirectory. Okay, it's already downloaded. It's fairly quick. I'm just going to close a bunch of windows here. And then I'm going to go to Microsoft Explorer and look at, let's see, map data. Here it is, map data. Map data under DEMS. Let's see, where is, no, I'm sorry, I've got to go to temp. I'm sorry. Those are all of these call signs are locations where I've got data for HFTA analysis. I've been doing this for a few years. Okay, let's see now. Where are we? Temp. Here's the temp file. Okay, so what we just downloaded was this beastie called ned_606881118.zip. I'm going to open it up using WinZip, and I'm going to take the file of interest, which is the TIFF file. I'm going to extract it. In this case, I'm going to extract it to the maps, cmapdata \dems. That's the standard default directory. It's done. Now let's go to DEMS. Oops. Go to DEMS, and here it is, the TIFF file that I'm talking about. Now I've done this previously, and I've downloaded that and labeled it to be W6YI-NED, but let's work with this this data file here. So what we do now is we bring up the microdem program, and then File, Open DEM, and we're going to open up this NED file, and there's Jim's QTH. Just exactly like you'd expect it to look like, right, Jim?
Yes.
All right, let's go back to the slideshow. We've downloaded it. Now, what the first thing that I normally do when is when I download a NED file, especially, is because it is seamless data. I want to make sure that the data makes sense, and the way to make it make sense is to check the contours. So what you do is you go down to, you open up the calculate menu, you go down to where is, and use your keyboard to enter the latitude and longitude of your tower. And so then you enter the latitude and longitude of your tower. Once you press OK, it will come up with this little tiny box, a little red square, which will show the location of your tower base. Then what you do is you go and you zoom in this little rectangle made of dotted lines. You can see it. You can't really see the detail on this slide, but trust me, that's called the subset in zoom. What you do is you start with the upper left-hand corner, and you press the mouse key, the button, the left button down. You drag a box. This is fairly standard mapping technology interface. And then you generate an area, a smaller area, a zoomed in area. Then you do overlay, source contours, feet, specify a interval for the contours. In this case, 20 feet is a good number. Press OK, and what it will do is it will generate a topographic source contours, and you can see if anything weird is going on in here. Like occasionally, sometimes you'll see contours crossing lines, which is obviously not possible to happen when they cross upon themselves. So let's do live demo for Jim's QTH. Back to micro. And we say calculate where is, okay, let's show his tower number 1, which is 16.5732, tab 6.9427 minutes. Okay. You see this little box here, this little red box over here. I'm now going to see this, which is subset and zoom. I'm going to look around it. There it is. And let's see. Let's do overlay, source contours, feet. Let's do 20 feet. We'll do it in a black color, and there it is. You can see that this location right over here on this contour line is the 1024, it's a 1025 foot line. So this one has got to be 1045. This one's got to be 10005. So these are 20-degree spacings in contour. The location of his tower is 5733, 6.927. And so there's the location of his tower. So Jim, if you were to look at this thing, would you feel pretty comfortable that this looks like your terrain?
Yes, Ken.
Okay.
Having looked at this for over several hours.
So what I showed before was in the direction towards Europe or in the direction toward the U.S. It looks like there's a slight rise. Isn't that right?
Yes, there is. I'm just down from the very top of the edge of the ridge.
Well, that's where you went for a 140-foot tower too, right?
Yes.
A very wise choice. Okay, let's go back to the PowerPoint presentation. Now, finally, you've got some data. What you need to do is now create the terrain profiles, and we're going to create them in 5-degree increments by doing calculate intervisibility view shed. Okay, that's governmentalese on creating terrain profiles. This little symbol right here, this view shed symbol, looks suspiciously like what in other places in this program is called a weapons fan. And obviously the program was developed by the military, by the U.S. Naval Academy, for the military primarily. And so they are interested in what happens when you shoot a weapon in various directions. What will you hit? Will you hit the dirt in front of the enemy, or will you hit the enemy himself? So you would click calculate intervisibility and then view shed, and then you specify the exact you double click on a point on the map, and then enter the latitude and longitude, the exact latitude and longitude of your tower. Then the next window opens up. You will name this, and then in this particular case, I'm in this non-live demo, I'm going to call it N6BV-NED. Click OK, and then what it will do is it will create 72 terrain profiles in increments of 5 degrees around. Now, what it does is let me go back just a second. I have a range that's a default range of 4,400 meters around the tower, about 14,000 feet, close to three statute miles, is enough area around the tower to give HFTA enough data to use properly. Okay, let's see. Then you'll save it. The files will be named with an extension of the number of degrees of azimuth. Like, for example, this is N6BV_1-260. That's 260 degrees azimuth, true. And it stores it as a default in the C map data / microdem project /fans file. Okay, so let's do Jim's location using micro dem. I'm going to open it up again just to make sure that I clear anything that's in there. That's now here. Okay, here's that little intervisibility sign, but in here it's called weapons fan. Same thing, intervisibility or weapons fan. Take your choice. Just don't shoot at Jim's tower, right?
Please.
Okay. Whoa. Let's see, intervisibility, view shed. Okay, now I'm just going to pick a point on the map because I will define the exact latitude and longitude now. 16.5732 tab 6.9427. Okay, and then I'm going to call this W6YI-Tower 1. Whoops, let's get this properly. W6YI-First Tower Ned. And it's going to suggest a location, which, as I said, is in the MD projects fans. I'll store it there. And now you see that it's created, it's difficult to see, but it's created a bunch of lines at 5-degree angles. The green ones indicates where it is not hitting any terrain. And these range rings are for 2,200 and 4,400 radius in meters from the center of the where the tower is located. Now, here's a little trick. If I double-click again, I can start working on the second tower. So let me do 16.5847, 16.5847, tab 6.9258, enter, and this one we're going to call W6YI-2 NED. We're going to save it in the same fans. We're going to now click again and do 16 for the tower number 3, 16.5778, tab 6.925, oops, 6.8911, sorry, 8911. Let me see, I'm on tower 1, 5778, good. Tower 3, so this is W6YI-3 NED. We'll store it in the same fans location, and then the fourth tower, we'll start here, and tower number 4 is 16.5666, tab 6.8815, 6.8815, enter. Name the last file is W6YI-4 NED. Okay, we have now characterized Jim's 4 towers using the NED database. Now let's go back to the... Now, this is a considerable, after a considerable experience looking at both NEDs and DEMs, I consider the DEMs, that is a digital elevation models, the second type of file which we're going to look at next. The topographic charts generated using DEMs are slightly better, in my opinion, than the National Elevation Database data. Especially when you get into rugged mountainous terrain. If you're in relatively benign ground that's not in the mountains, either DEMs or NEDs will work fine. But when you get to really critical things, I prefer the DEMs. But as I said before, one of the pains in the neck of using the DEM files is that you have to merge. You may have to merge as many as 4 of the USGS 7.5 minute quads to get the full 360-degree coverage out beyond 4,400 meters around your tower base. So, and after merging the DEMs, it's a good idea to do the contours just to make sure. Okay, the technique is to find, first of all, the names of the quad topographic maps. And the USGS, or the world, uses some pretty interesting names. They're not very obvious. They're probably named after people more than anything else. So what you do is you go to a wonderful website called MapMart, and the URL is this one. It's also in, you can click on the URL in the help file. And what you do is you zoom to an address. And again, in this particular case, I'm using as a demonstration 32 Beacon Hill Road in Windham, New Hampshire, my old QTH. And what you do is you zoom out. What it will do is it will place a star, a red star, where the location is, the street address is. And you notice in this particular case that this is the Windham, hence the name of the town is Windham. The Windham, it's placed just about in the middle of the quad, but it's up from the center of the quad in the latitude direction. So what it would seem is that if I create a circle of 4,400 meters around this point, I will run out of data in the direction of Derry. So in other words, I should download and merge together Windham and Derry. But just in case, you'd want to download and merge Salem Depot and Nashua North as well. So these 4 names would be, in this case, downloaded. Okay, so let's run a live demo for Jim's location. Let's see. The map mart is here. Zoom to drop-down box address. Jim's location is 10250. What happened there? Second. 10250. What is the rest of it, Jim? Paso, Paso.
Paso, yeah, P-A-S-O, and then Flora, F-L-O-R-A.
Okay, and the
Escondido.
city Escondido, Ca
92026.
92026. We don't really need that, but we'll go there anyway. So when you press zoom, it now cogitates a little bit, works on the internet, and places a star right where the entrance to your house is, or rather the entrance to your driveway, I guess, right, Jim?
Yeah.
Okay, now we're going to zoom out so we can see the names of the topographic quads. They're not showing yet. We're still zooming out. If you leave the cursor right at the arrow and click, it won't do anything. You've got to go off it, then come back again. Don't ask me. That's someone's interesting way of programming the way the cursor operates. Okay, now we're seeing the Pala. Is that pronounced Bonsal?
Bonsal.
Bonsal, okay. And we can't quite see these ones, so let's zoom out just one more time. Okay, so what we see is this is the quad, the map called Pala, P-A-L-A, and you'll notice that the shim's location is in the lower left-hand side. It's in the southwest side of it. So in order to get enough data, I'm going to need the Bonsal, the Pala. It looks like I'm going to need Valley Center and San Marcos also. So let me write those down. Pala, Bonsal, San Marcos, and Valley Center. K6NA is in Valley Center, isn't he?
Yes, about 7 miles away.
Yeah, that's what I thought. Okay. Now let's look for the national free GIS data. I logged in previously to my account number, which is a free account number. Let's go to California. Now, the first thing it asks you is the county in California. In this case, Jim's in San Diego County. And what we're looking for is the digital elevation models, the DEMs. Now, when it says DEM 24K, what that means is that's the scale factor. In other words, 1 inch is equal to 24,000 inches on these so-called quadrangle 15-second maps. So, which ones are we going to need? Well, Bonsall was the first one. It's right here. Now, the free download is the green button. You got to pay for higher speed with the brown button, so I use the green button. Oh, I guess I have to go log in again. Excuse me, let me log in again. Since I logged in a couple of hours ago, it's probably not happy with me. So it unlogged me. The dangers of live demonstrations. That's what I was worried about. Okay, let me get back to this and log in my account. Log in. Okay, here's my login. Now I'm going to go back. Okay, and start in California. Did I click that? California. This website is kind of slow now. Other people are probably using it right now. Go away, everybody else. I'm demonstrating something. Well, the website's not responding very well. Huh. Let's see. Well, I guess I'm going to have to abandon this right now because the website is not responding. Let me go from the beginning just one more time. Let me go. No, it's not responding. So anyway, this has been going remarkably well. It's amazing we got to this point. So what you do is you click on California. You click on in this case, San Diego. You go for the digital elevation models, the DEMs, and then you download these DEMs. And in this case, we download 4 of them and select them one at a time. Now, very often you'll find that there's the most commonly available data format is 30 meters resolution, and that's the one you want to use. But sometimes the later versions are in 10 meters. Well, 10 meters will work. They take much, much longer because they've got much bigger files necessary for the 10-meter resolution. So use 30 meters if possible. Then what you would do is you download each one of them. You download each one of them, and then you save them into the appropriate subdirectory. Then what you do is you go to open microdem and use data manipulation. DEMs pick single for the merging, and then you click on the various files that you want. What happens is you click open, and then you click the second one, open, the third one that you had in this case, then the fourth one, and then when it's digested those 4 files, then you say cancel. Oops. Then you say cancel, and it will prompt you for a name to save the data as your file name of choice. Now, what I've done is I have previously downloaded Jim's information and stored it as a DEM. So what I'm now going to do is show you actually how to use the DEM data, how to actually bring it up and look at the source contour first of all. This is his DEM data. Looks familiar, doesn't it? Because it looks very similar to the data for the NED file. And calculate where is 16 for tower number 1.5733. 117, 6.9427, 6.9427. There's our little box right over here, and what we want to do is zoom in on it. Now, the reason, by the way, that we go through this zooming in business is that if you try to use a large map, a large area, and show the contours, it'll bog the computer down completely. In fact, it sometimes will lock it up. So you don't want to, let's see, overlay. You don't want to, you do want to go in and look at a smaller map size. And there's the terrain. Again, the terrain is very similar for this location between the NEDs and the DEMs, but I would still trust the DEMs more. Finer, just that they've got a database that's been around for a longer period of time. And when you make a seamless database, what happens is that you will very often make it too seamless. All right, so let me bring up. Let me see, how are we doing on time? We've got about another half an hour or so. Is that right, Ken?
Well, this can run as long as we'd like, so
Okay.
It's entirely up to you.
Until they fall asleep out there, especially in Europe, huh?
Yeah, there you go. I'll have to go to work.
Or have to go to work. Yes, indeed. All right. Now, what I want to, let me do a weapon span, which I'll just show you is the same thing as intervisibility. And what I want to do now is specify using the NED, using the DEM file, tower number 1, 16.5732, and it's easier to hit the tab key usually, 6.9427, 6.9427, enter, and then we're going to call this W6YI-1. I'm not going to name it as being a DEM, but that's what it is. I've already identified the previous terrain profiles as NED stored. Okay, now let's do this. Let's open up HFTA. And what I'm going to do is look in the directory where it's stored, which is in map data, projections, fans. I'm going to look in the direction of, let's say, towards the U.S. for the domestic contest, the sweepstakes contest. I'm going to next show the NED file in that same direction, which is 65 degrees. And then what I want to do is I want to compare the two terrains. Now here this is NED is in red, so to speak, and blue is the DEM file. I can blow this up by expanding this area. You can see that if you look at the terrain, at a tower height of 50 feet above this particular tower is Jim's stack on 20 meters. Let me show you what happens if we. This is the HFTA response. This is for, the green one is for a flat ground, which I always use as a reference. This is his stack at 150, 5 elements at 155, 150 feet. This is what a flat ground response will be. Now, in comparison, the NED file with the same antennas, same spacing, looks like this. It's fairly close, but at the left-hand lower edge, it's a little bit less because there's some blockage going on here. And the blue one is the terrain from the DEM file, which is the one that I would believe actually more so than the NED data. Okay, let's see if I can find out where we are in this presentation. We looked at the contours. This is an illustration of a contour from K1KI on the East Coast in Connecticut. This is the NED, the seamless NED, and this is the DEM file. And you can see that the DEM, it looks smoother. This is a little bit jagged because of the NED seamless data. This is a comparison for W1 WEF. And over here, there's a very interesting thing where the contours actually cross over themselves. And in theory, a contour is not capable of crossing over itself like that. All right, so those are for the USGS, for the United States guys. The USGS DEM files and the NED files are readily available. The microdem version bundled with the ARRL antenna book, that is on the CD-ROM, is version 7. It will not do the shuttle, the space shuttle data. That requires a later version after, in fact, dated after, in fact, June 5th, 2009. I worked with Professor Guth to get that working properly. So, if you need the latest version of microdem, it's about 60 megabytes in data, so you'll need a relatively fast internet connection in order to bring that in. I've been demonstrating the latest version of microdem, although you won't see much of a difference between the version 7 and the version 10 in terms of the operator interface. Okay, so for you guys out in Europe or in the South Pacific or Asia or wherever, the U.S. government has released digital terrain data from the Shuttle Radar Topography Mission, and it covers about 80% of the world. It's between 60 degrees north and 54 degrees south latitudes. That means that it won't cover Antarctica, it won't cover the guys in the northern Finland or Sweden, but it will cover about 80% of the world. The data is available in U.S. territories or in the continental U.S. with a resolution of 1 arc second, which is about 30 meters. Outside the U.S. and U.S. territories, the U.S. government has restricted the resolution, as I said, to 3 arc seconds, which is roughly 90 meters. And what you do is you use this URL down here to select the data coming from the basically this is data that's been massaged by King's College people in London. I generally select the USA server to bring it, and what you do is you on this world map, you select a point, rather an area here that covers the area that you want to use, and then you click begin search, and down, if this is the data area that you want, for example, this is showing the middle part of the UK, of Britain, Great Britain. And you will save it as a GeoTIFF data to disk, just like the NED file data, and create your own profiles. Okay, let's see if we can, if this is going to cooperate with me tonight. It's SRTM data search. Let's say we wanted to download Jim's data, which is probably this area right here, 33, 170. Yeah, this is the latitude minimum is 30, the maximum is 35. Jim's latitude is 33 degrees. The longitude is bracket by 115 and 120 west. So let's download this data and save it as an SRTM 13-_06 zip. This will store it. This is about 20 megabytes of data necessary. I can do a tap dance here while we wait for the data to be downloaded. Let me show. This is you may very well be interested in if you take a U.S. location. There is not only the DEM data, but the NED data, as we went through. There is space shuttle data available in 1 arc second, the same degree of resolution as the NED and the DEM files, and also 3 arc second. So how well do the topo sources agree? Well, this is showing the plot of the terrain data for all 4 types of data, and it shows that the SRTM data, the space shuttle radar data, is usually, not always, but usually higher. In this case, it's higher by about 50 feet, which just happens to be the treetop height of location in New Hampshire, where N6BV was located. The radar sees treetops. It also sees large buildings. And so consequently, in general, if you have trees, heavy forests, the data will be different, although the slopes, which is what really works in diffraction analysis, the slopes will be roughly right. Let's see how we're doing with our download. We're 51% there. It's still going. Okay, let's go back to the non-live demonstration. This is the HFTA responses calculated using those 4 terrains, the 1 arc second, the 3 arc second shuttle data, and the NED data, and the DEM data. So I point out that a man who has 2 watches is never quite sure of what time it is. That's an old Chinese proverb, I understand. I trust the good old-fashioned DEMs the best myself. Okay, now this gets into, okay, I finally somehow, whether it be by shuttle or by NED, seamless database, or DEM, 7.5 minute database, I've got terrain data. Now, how do I use it in HFTA? First of all, I'd like to give some perspective on terrain. When you do the HFTA and look at the terrain profile, clicking the button on for terrain profile, what the program does is it automatically sets the X and the Y axes so that you can see the maximum change to show the change most vividly. In this case, this is for W6NL, a huge station up here in Northern California, who lives on the top of about a 3,400-foot mountain, and whose terrain goes down to almost sea level, or maybe about 500 feet or so, 3 miles away. Now, if you were to do a little trick by putting a flat ground at 0 feet, and an antenna that's 1,440 feet high, 14,400 feet high, what you'll get is a true perspective. This is how his terrain looks if you have equal X and Y axes, Y and X axes, and plot them. So this is most terrain, frankly, when it's not as dramatic as in W6NL's hillside terrain or mountaintop terrain. Most terrain looks like it's a slightly bumpy straight line. because the slopes are not as big when you use the true perspective. So that keep that in mind, that this is also this, but this is a true perspective, and this is a perspective meant to show the changes. Okay, by the way, I think we finally downloaded that that data, and it will be placed in my temp subdirectory as SRTM. Well, I guess I downloaded it before, but what you need to do is you need to, again, extract the TIFF file, extract it. We'll put it in the DEMS. It's already there, so I'll just overwrite it. And now, just like any other thing, any other data source, you open up Microdem, open up the SRTM 1306 TIFF, and there it is. This is the Southern California down to, I guess this is Los Angeles area right over here, and San Diego area right over here. So just to show you that Microdem will read shuttle data, version 10, as the later versions will read shuttle data as well as other data, NED and DEM data as well. All right, so what can you do with HFTA? What can you change? What can you vary to cause things to happen? Well, the first thing you can do is you can change the height of the antenna above ground. You can stack Yagis, as many as 4 stacked. And it assumes these Yagis are identical, by the way. You can change the number of elements that you select in the Yagi, and thereby change the gain of the Yagi. It goes all the way from a dipole to an 8-element Yagi. That is an 8-element Yagi on 20 meters with an 80-foot boom, so it pretty much covers the range of possibilities of antennas that you can use. You can change the spacing between stacked Yagis, and you can actually move the tower back from a cliff or from a hill and see the effect of changing the foreground to flat ground before it hits a cliff or a hill. You can also do so-called BIP-BOP analysis, which is showing both in phase or both out of phase. Those who have used HFTA before or who have been watching very carefully this presentation will see that there's something called a figure of merit in HFTA, and it is the gain at each elevation angle multiplied by the elevation angle percentage for that angle, summed and averaged over all angles from 1 to 35 degrees. This is, let me get my cursor back. This is the figure of merit for BV, and the picture we just saw about the various terrains, profiles from DEM, NED, SRTM 1 and 3, arcsecond, the data sources. So the figure of merit is this kind of a statistical weighted gain because it uses the elevation angle statistics and calibrates the overall response into a single snapshot kind of number to look at. Let's see. Now, for example, this is a situation where K1 KI's got a stack on his 40-meter tower of 3 5-element 10-meter beams at 130 feet, 95 feet, and 80 feet. On another tower, the 10-meter tower itself, he's got a 6-element, 68-foot high tower, 10-meter beam. And the one in blue is that 10-meter, 68-foot to 10-meter, and this is the stack. Well, you'll notice that the figure of merit for the stack is 15.8 dBi compared to the figure of merit of 14.7 dBi for the single Yagi. However, the single Yagi does not have, at this point right over here, an extreme null that the stack itself has. And consequently, even though the stack has a higher figure of merit, there are times, in fact, the time when the angle is most likely to occur, the highest angle. Let me back up just a second. What this bar graph is showing is it's saying that almost 13% of the time when the 10-meter band is open from, in this case, Massachusetts to Europe, 13% of the time it occurs at an angle of 9 degrees. So statistically speaking, the most likely angle that propagation between Europe and the east coast, the northeast coast of the U.S., would occur at 9 degrees. And this just happens to be where this stack has a huge null. So what it's saying is that you've got to be careful with looking at figures of merit only, because they're a two-edged sword. They give you a basic idea of how an antenna system works, but they at the same time can fool you because you miss things like having these large nulls in the response. All right, so furthermore, the FOM, the figure of merit, will vary depending on the target receiving area and the frequency band. And so, as I've been showing in all of these demonstration graphs, HFTA graphs, you should also show the figure of merit over flat ground so that you've always got a reference on what's happening. Okay, what happens in HFTA when there's a hill in the way? In this case, this is a hill that's 460 feet compared to 320 feet, about 140 feet higher than the tower base. But it occurs 8,000 feet away. There's also a close-in hill, a slope downwards of about 70 or 80 feet within 2,000 feet of the base of the tower. So what happens? What does HFTA say is happening here? In this case, we put on K1's KI's, this is K1 KI's location. He's on 15 meters. He's got a rotatable tower with a stack of 90, 60, and 30-foot 5-element Yagis. So comparing a flatland set of the same Yagis, 90, 60, and 30 feet, 5 elements each, comparing that to the actual response that HFTA calculates, it shows that this boost in performance at low angles is caused by this slope right over here. This hill, 8,000 feet away, has relatively little effect. So the big hill far away doesn't affect much, but the close-in response is determined by the slope close to the base of the tower. Okay, now steep mountain drops. Tower heights done over flat terrain are pretty easy to optimize. It's interesting to note that most of the big multi stations like K3LR, like N6RO, like W3LPL, most of those big stations are located on relatively flat ground because it's fairly easy to optimize. Mountaintops can be real tricky and they can be very non-intuitive. For example, this is a situation at W6NL's place where he's got a very steep slope, almost 14 degrees from the base of the tower downwards. And for a 40-foot high 6-element Yagi at 15 meters, the response is fairly flat out to about 16, 17 degrees of elevation. But if you go to if you were to stack an 80-foot high Yagi over that same 40-foot lower Yagi, you'll get more gain lower, but you'll start moving gain up at angles that are necessary, in this particular case from W6 San Francisco area to the U.S., to all of the USA. So it's possible to be too high on a mountain, and that gets exacerbated by situations where you're putting 10-meter Yagis, especially, can be very easy to put them too high. Watch out for nulls, as I illustrated before. And nearby saddleback terrain can be killers too. The term saddleback refers to looking at the side view of a horse's saddle. Where should we go? This term here looks like a saddleback. In this case, there's from K1 KI's 15-meter tower. Again, this is called a saddleback because it looks like part of a saddle, the aft side of a saddle, as you look at it from the side. There's a nice overall drop-off from 30 feet, for example, down to here, but there's a bump in the terrain in the direction. What happens? Well, again, comparing 30, 60, 90 foot stack over flat ground and the 30, 60, 90 over that actual ground, you'll notice that there's a hole in the response over here because of that saddleback. Now, let's put this in some perspective. If you were to put a 3-element Yagi at 70 feet over flat ground, you know, a fairly typical kind of ham installation, you'd still be, that Yagi would have a gain run like perhaps as much as 12 dBi versus at the worst case a 13 dBi gain that this stack has into Japan from K1KI's place. All right, there's another thing you have to watch out for. You have to watch out for so-called aliasing glitches. This is a ray tracing program, and most ray tracing programs have things when the various components making up the overall response just happen to align wrong, you'll get glitches, either deep nulls or high peaks that don't actually exist. So what I suggest you do is you check your response in 1 foot increments. For example, this is the very steep and complex terrain at N2IC's place he's in New Mexico. There's a very steep drop-off from 6,850 feet down to 6,450 feet in maybe 1,500 feet away from the tower. There's complicated diffraction or things that go on over here and here and here. And if you, for example, put a 5-element Yagi on 15 meters, one at 59 feet, 60 feet, 61 feet, and 62 feet, a 1 foot increment in change should not cause large changes in the response, but yet they do. So that indicates that there are some unrealistic changes due to aliasing. You should check that anytime you do HFTA analysis. All right, make sure you check for aliasing, validate the terrain profiles, as I say, particularly when you're using the NED data, seamless data sets compare it to the real world. Different directions can give different responses. For example, this is K1KI's 15-meter stack pointed at Europe. That's the terrain in blue, compared to the same rotating stack when it's pointed at South America. And here are the calculated HFTA results into South America as the red one. Because of that terrain, he's got gain that's in moon bounce territory. He's got a peak gain at about 5 degrees of 23 dBi. You'll notice that gain does not come from nothing. What is stolen from this area right over here compared to the flatland is used to pump up this area right over here at lower elevation angles. That's how gain occurs. You squeeze the pattern. All right, so I'm trying to rush through this here now. The best terrains, flat terrain is easy. Gentle terrain, such as my old location towards Europe in New Hampshire, they're very good for smaller Yagis such as tribanders. I have very good results from tribanders. Steep terrain, mountainous type of terrain, sometimes does not allow easy stacking on 15 or even worse on 10 meters. It's far too easy to be very high, too high to control the response at angles, especially higher elevation angles that you may need at times. Do model your antennas just to make sure, especially before buying a property. That's where HFTA really comes into its own of finding properties that have problems. Some generalizations about terrains is physical constraints such as tower guy wires. They limit the places where you can place stacks on a tower, especially larger antennas. They have to rotate under guy wires, for example, when they're on the intermediate portions of the tower. Okay, the antenna models, the Yagis used in HFTA are very simple. They do not exhibit interaction between them. They're like point sources, if you will, mathematical point sources. So that you want to space the Yagis more than about 20 feet, more than about a half wavelength, which is 30 feet on 20 meters, in other words. Bit bop, both in phase or both out of phase, can occasionally be useful. Here's a situation where I've taken K1KI's 15-meter stack. I've I've actually added another antenna at 120, 90, 60, and 30 feet. And this entry right over here, 120 asterisk, indicates that I'm telling the program to phase the 120-foot antenna, phase it 180 degrees out, and that's the red response when it's 180 degrees out of phase, and that's the response when all the elements, all the Yagis rather, are in phase. Okay, now HFTA and VOA area is where things come. An area coverage map can be very helpful to visualize contest performance in a target geographic area. There's a program that's included with HFTA. It's in the same subdirectory as hfta.exe, but it allows you to convert an elevation response due to terrain to a VOA cap antenna file. And I should note that there's a file called out.prin that's created every time you run an HFTA calculation and then go back to the Windows operating system. When you close HFTA, it saves this file called out.prin, and if as many as scenarios that you've calculated, it will save them all into that same out.prin file, but only the first one will be used when you use the make VOA program. This is a situation where LZ9W is putting up new stacks to supplement the existing Yagis on the hilltop location that they have in Bulgaria. This is a calculated response of what his new stack, the blue, their new stack, not his, the LZ9W's new stack in blue compared to the existing Yagi, which is a single 6-element Yagi on 20 meters, located on the small tower on the roof of the hotel that they operate from. Okay, this is a view of the input screen on Make VOA. It's a DOS program. Sorry about that. It's subject to the same limitations of having 8 or less characters. So that's the DOS limitation for an output file name. What it results in when you run that program is it takes the first computation out of the out.prin file and creates in this case, a LZ9W-20.ele file. Then you use that as an input to VOA area, is a transmitting antenna, and this is the resulting signal coverage for LZ9W with their new 20-meter stack. This is assuming that the same response for the stack occurs in every direction. That's it's a little bit of an anomaly, but the heading line for where you're pointing that Yagi is actually along here in this particular case. So that plus or minus 20 or 30 degrees would be the nose bandwidth of any kind of practical Yagi on HF. Let's see now. This is the resulting angle coverage. This is comparing the LZ9W's situation versus a more typical, this is like a 3-element 20-meter at 55 feet high above flat ground. You can see that in the direction here pointed into Africa, for example, they got a far, far larger signal because of the stack compared to a single 3-element Yagi at 55 feet over flat ground. Okay, what we have covered tonight in rapid detail is a brief description of HFTA, how to get terrain data from 3 sources on the web, that is NED, DEM, and SRTM shuttle data. Run through a bunch of hints and kinks for using HFTA, including how to use Make VOA program to create antenna files for VOA area. Now, let me try to keep this in perspective, guys. It is very easy to get very involved, even consumed in antenna modeling and terrain analysis. So if you are already S9 plus 20 dB into Europe, you might require bulldozing your terrain to get another 2 dB of gain. And this would result, finally, in its S9 plus 22 dB signal. Now, but in a pileup or at the noise level, 2 dB can be a big deal. So maybe you should get your bulldozer ready instead. I think I've run to the end of my time limit. Ken, You want to do some questions from now?
Sure. Okay. If you're ready for that, we can take some questions. As mentioned earlier, two options for submitting your questions. One is on your control panel. And again, if you don't see the bigger control panel on your rectangular grab tab, there's a double arrow at the top. Click on that. But in the control panel, you have a questions box. So click on that, type in your question, hit return, and we'll pick that up. Or if you would like to speak directly to Dean, you can raise your hand, and I'll unmute your microphone and call you.
Perhaps it would be most fair to ask Jim if he's got any questions.
Yeah.
After all, we've been using his vision as an example.
All right, I had Jim muted there for a second. Jim, you have anything else to add?
Oh, no, Dean, definitely get to everybody else's questions so they get any other benefits they need.
Well, I could spend another couple of hours analyzing antennas and what you've done at your location, but we don't have that much time.
Okay, well, the first question is, how much more accurate is the SRTM data for rugged terrain locations than the regular DEM or NED?
Well, I would say it's less accurate because you don't know what kind of forest that was present when the space shuttle passed over that and looked downwards with its radar. So, if you don't have to use the SRTM data, then you'd be better off in the U.S. and the U.S. territories. You'd be better off to use the DEMS. But
okay.
if it's the only thing that's available, like if you're in Italy or something, or you're in Bulgaria, well, it's certainly better than trying to do the data by hand.
Okay, good. Next question, were there any changes made to HFTA from the 20th to the 21st edition of the antenna book?
No, the 21st and the 20th have the same basic version of the runtime DLL, so they act the same.
Alrighty, next one. Can you take an antenna model from EasyNet or similar and use it as an antenna for HFTA?
No, as I was explaining earlier, the mathematical model of the antennas used in HFTA is a simple point source. We call it a point source with gain. So you'll find that the range of that what the terrain does is a lot more than just the simple gain of the antenna or the pattern of the antenna itself.
Okay, Mr. Brown is wondering, can we enter multiple angle responses into make VOA?
I'm not sure I understand.
Let's see, I think we had Jim, as a matter of fact, I think we had you testing your microphone before, so why don't I unmute you. Jim, you there?
Yes, indeed. I think I am.
Yeah,
you hearing me?
Yep,
Yep, hearing you, Jim.
Okay, great. Yeah, the thing I'm getting at is, let's say that you've computed, what Make VOA does, as I understand it, is model your response onto a map with VO ACAP, right?
Yeah,
so
what it does, it creates an omnidirectional pattern but whose elevation response is appropriate to the terrain that you just analyzed.
Okay. Well, the thing I'm getting at is that if you've got different terrain in each direction, as I do,
Yeah.
as many of us do,
Yes, indeed.
out here, is it possible to shove multiple responses into VOA and get a map that varies with direction?
Jim, you're not the first guy that's thought about that, believe me. It's bugged me for a while, too. And in my copious free time now that I'm retired, I'll someday get to that.
Okay. Thank you, sir. And by the way, I am a guy who absolutely believes in the usefulness of this. I found it correlates quite well with my on-air experience.
Very good, Jim. Thank you.
All righty. Let's take another question here. Regarding the elevation angle statistics that are in the ARRL, it was the antenna handbook, wondering how those were obtained. I think those are the calculations you did, right, for the various call areas.
Basically, there were computers going 24 hours a day for a couple of weeks back in the early 90s, generating these elevation statistics. I've generated new ones, updated ones that have more coverage area. Take a look at the ARRL website and do product notes. and there's a, or you could just search the database, search the ARRL website to find the URL to get the latest data, the latest elevation data. But it's subtly different than the old stuff. But basically, the idea is that you've got to cover all of those angles if you want to be effective at any particular time.
Okay, I see we have at least one hand raised. Bear with me for a moment. Question, can you enter vertical antennas or vertical arrays?
Now, HFTA does not do verticals because the trouble with verticals is that they require the ground constants of conductivity and dielectric. They require those ground constants at each point along the stroke of an azimuth radial, and consequently, I mean, it can do seawater in that sense, but other than seawater, a vertical over complicated terrain just doesn't. The data is just not available to do a proper evaluation. So HFTA only does horizontal antennas.
All right, Jim, W6 Echo Bravo, you are unmuted. Go ahead.
Okay. You hear me okay?
Sure. Hey, Jim, how you doing?
Okay, I'm doing great. Dean, thanks for putting this on. It's very informative. I sent you an email this afternoon pointing out something that I had observed with the older, I think it was out of Antenna Book 19 version of HFTA, where I was looking at the performance of an antenna at 40 meters over my somewhat steep terrain that you're familiar with. And I just stumbled across it when I changed the frequency very slightly. Things changed very radically.
Yeah, and what is happening there, Jim, is that some of the what's so-called pre-smoothing that's done on the terrain is a function of the wavelength, and you just hit a critical point where the frequency changed enough so that the wavelength changed and probably knocked out a diffraction point, in simplifying the analysis, doing what's known as a Rayleigh criterion on the analysis. The actual change was not a whole bunch. It didn't really change the response all that much, so I wouldn't get worried about it. I'm looking at that whole algorithm for the next revision of HFTA sometime when I get the chance to do it.
So to make sense out of it, should I try to just kind of merge the two in my small brain, or?
Yeah, that's what I do.
Okay, well, that'll probably make it pretty smooth then. Thanks a lot, Dean.
All right, Jim.
All right, very good, Jim. All right, let's go to Hawaii. Bill, King Henry 6 X-ray Sugar. He says, when you made my terrain files, which did you use? NED, NED, DEM. By the way, the program is right on the money as far as the performance is concerned, and I would have to agree. Bill is pretty loud over here in the East Coast.
Yeah, he's pretty loud in the West Coast too. Hey, Bill. I used the DEM files.
Okay, good. I was hoping we wasn't gonna have to get out there and start moving antennas around or something. But all right, another question. Do you recommend close-spaced Yagis on the good-sized hilltops for the fullest pattern on the higher bands?
Well, if you've got a really complicated mountaintop terrain, with very steep drop-offs, you'll find that on 10 meters and 15 meters, you almost want to put the antenna down below the base of the tower. Obviously, you can't do that. But about the only solution you have, because going up high is not going to help very much, is to make longer boom Yagis in order to get the gain. And that's indeed what a guy like W6NL has done. He's placed towers around his flat part of his mountain in the directions of interest into Europe or Japan or the U.S. And he's made like a 60-foot long boom on 20 meters. It's only about 35 feet high. It looks kind of ridiculous, but boy, does it play.
Okay, I think you may have answered this one already, but it's come up a couple of times. And what is the latest version of microdem?
The latest version is somewhere in some version of number 10 or version 10. Anything after June 9th, I think it is, 2009, will work properly with the radar, the shuttle radar data. The older version, which is the one that's actually on the CD-ROM that goes with the 21st edition of the antenna book, the older version is version 7. It's in fact I think 7 alpha. It will work fine for U.S. use. You don't have to worry about going to version 10. The instruction manual gives explicit details on how to set up both version 7 and version 10 for the initial installation.
Okay, we're covering some ground tonight here. We're going to head over to Europe, and Zoran, Y1 Echo Whiskey, is wondering if there's any problem if they use Google Earth for collecting the terrain data. So if we move the cursor with the ruler activated, we have exact distance from the tower, and we see the direction and altitude data for any point shown.
Yeah, well, that's kind of doing it manually. It's possible, Zoran, to do it manually like that, but the basic underlying data that Google Earth is using is shuttle radar topography, modified shuttle radar topography mission data. So you may as well use the SRTM data directly and not have to do it manually.
Okay, let's see, Key6 Victor Alpha, at this part of the sunspot cycle, should we be looking more toward the lower angle elevations or higher ones?
Hi there, Rick. You're going to, at this point of the solar cycle, be as it may, the angles tend to be lower, but you know, in another couple of years, hopefully we'll have 10 meters open again, and then the angles will tend to be a little bit higher. So if you want to cover all the angles, you're going to have to take appropriate responses for both high and low angles.
Okay, let's go to W2GD. John, you're unmuted. Go ahead.
Hello, John.
Okay, John. Sorry, we're not hearing you. You may want to check and try back again. I will put that back on mute, and let's see here once. Okay, W8 Tango November. I live on a hilltop which was 30 feet higher 3 years ago. Okay, my tower is below the current top of the hill. Do I need to modify the DEM data in the directions facing the now shorter hilltop?
Goodness, 30 feet. It sounds like a volcano you live on. I would do the contours, you know, as I've been showing with either the net or the DEM data, and see if it no longer if it no longer reflects what you've actually got, then you're going to have to go in there and manually change the data. But the shuttle, well, let me see. I mean, most of the NED stuff seems to be relatively recent. You might find that it falls within that 2-year period when the mountain went away.
Okay, here's another one. When I used HFTA on a relatively flat terrain in any Massachusetts, I guess it's northeast, I found single Yagi will work the best at about 50 foot high. When you go higher, the FOM drops. Is this normal?
Yeah, it definitely is higher because the lower lobe is shrinking when you put the antenna up higher. Consequently, if you've got angles that you need to address above about 10-15 degrees in order to cover geographic areas that you want to cover, you know, going up higher will reduce the FOM, definitely. But again, be very careful on FOMs. They're a double-edged sword. They're potentially dangerous. You know, it's like having a hammer as your only tool. Everything begins to look like a nail after a while.
Okay, Mr. Brown wants to know if you can show how to move a tower.
Oh, okay. Is that you again, Jim?
Yep, it is. I can actually unmute him if you'd like.
Okay, what I'm going to do is show W6YIs. I'm first going to cancel and get rid of that line right here.
Jim, I've got you unmuted too if you want to hop in.
Okay,
yeah, no, that's all I need.
Okay.
Okay, what I'm going to do is, this is the terrain for W6YI on towards the U.S. And what I'm going to do is options, move tower. I'm going to move the tower back 1,000 feet just for fun. And let's see what it looks like. And what it will do is save it in the second slot. Now let me make sure we've got the same antenna. And let's plot the terrain. You can see 1,000 feet is moved back. What height was at the beginning, I've added 1,000 feet of flat land into it. Let's see what it does in terms of computing the. Okay, so what it's done in this particular case, it's moved the tower far enough away from the hill that it actually improved the response. You can see the red line is the one with the 1,000-foot extra flatland before going up this little saddleback over here. So it's actually improved the response a little bit. In this case, it's about 0.3 dBi on the figure of merit. Does that answer your question, Jim? Guess he went away. You still there, Ken?
Yeah, it would help if I, I'm sorry, I muted myself. And I muted Jim. So, Jim, did that take care of your question?
Yes and no. It shows me what move the tower does, which is great and very useful. But I was thinking of actually a different tower location. So it looks like I got to go back into microdim to do that.
Oh, yeah, absolutely.
Okay, that's it.
All righty. Tom is wondering if HFTA is useful for very flat terrain.
Well, yeah, it's useful to show you what the effect of height or stacking does to the angles that you need. It's just a lot less challenging to do.
Let me see here once if, okay, in K6 VVA, did you have another question? Your hand was raised. I don't know if that was from an earlier one or not. Go ahead, Eric.
Hi, are you copying me?
Yep, sure, go ahead.
I thought you were a CW guy.
Yeah, I am primarily. Hi, Brodeen. Got a question on the future edition of HFTA. Would it be possible to enable us to put in a range of elevation angles to generate a figure of merit? The reason I asked is from out here, for example, on 10 meters, if I remember correctly, most of the elevation angles are between about 0 and I think 15 or something like that. Or in some of our targets to certain parts of the country or the world, they seem to congregate between about 0 and 20 degrees.
Let me actually do something here, Rick.
Okay.
Let's see here. I've stored the newest elevation angles in kind of hard to find place for me even. But let's see.
How about W6 to US, 10 meters?
Okay, we'll do W6 from San Francisco.
Yeah.
Now let's do Europe. That's more challenging from San Francisco. And
especially right now.
Right. Well, it's impossible right now, so that's a challenge, I guess. This is what you're seeing on the screen is the elevation statistics for San Francisco. It says that almost just a bit over 18% of the time, the angle is 9 degrees into Europe from San Francisco when the band is open from San Francisco on 10 meters. So virtually probably 90% of the time, the angle is less than 9 degrees is what it's saying, and it goes down as low as 2 degrees. So does that answer your question, Rick?
Well, let me ask you this. The figure of merit, though, is still well, yeah, there's hardly anything between, let's say, 15 degrees and nothing between 15, well, a little spike there around 32. I'm thinking more actually in, let's say, towards the U.S., and it might have been 15 meters. It seems that the things pretty much taper off over 22 degrees or 24 degrees.
Let me bring up the U.S. numbers then. W6.
Yeah, maybe I'm not recalling this directly, but to be able to enter a range in, like if we had a specific interest in whatever it was that we could say, hey, give us a figure of merit only for the range between 0 and, maybe 20 degrees.
Well, that's not statistically valid, I don't think.
Oh, okay.
I mean, if this range of angles, what I brought up is the USA on 10 meters, the angles go all the way up to a maximum of 33 degrees down to 1 degree.
Right.
So,
but isn't the primary? I'm sorry. Go ahead.
No, you go ahead.
I was going to say the primary, as far as I'm concerned, I would only be concerned about like 0 to 18 or 0 to 20 degrees.
That's practical.
But the calculations are done 0 to 34 degrees, right?
Yeah, but so the numbers are so small up there that they don't contribute all that much.
Because I was look at the difference of the one null and the red bottoming out and staying down there where for a couple degrees compared to the blue. Maybe I'm getting too anal about it.
I won't answer that.
Well, the range. If it strikes your fancy to give us the capability to put in a range, it would be awesome. Thanks, Dane.
Well, okay, Rick. That is one thing, by the way, that in the calculation of the elevation statistics, the assumptions made were that the receiving antenna and the transmitting antenna were isotropic. That is, they had no nulls in their responses. Call it a misnomer, isotropic antennas with gain. But the idea was to find if the 10-meter band is open to Europe using a 2 F2 hops, let's say, that might take off at an angle of let's say 2 degrees from California, whereas a 3 F2 hops might take off at 5 degrees or something like that. Each one of those angles is a valid hit. It's all put into buckets or bins, and then the percentage as a total of the total is calculated. That's how these elevation angles were computed. So if you have terrain that blocks angles from happening, then your statistics would be theoretically different than the elevation angle statistics that are published by the ARRL.
Okay, Don says, I'm trying to download a DEM. The link in the instructions for HFTA from the 20th edition seems to be incorrect. I am getting an application error when I go to the link.
That is why I suggested at the very first is that you go, in fact, let me go back right to that. Go to the ARRL, go to the ARRL website and click on the menu Support Product Notes, or you can go to this URL down over here. But go to Product Notes and then click on 21st edition, and then click on HFTA, and it'll give you the latest instruction manual with all detailed instructions on how to do both the old version of microdem and the newer versions of microdem.
Yep, okay, he said he got it. I got one question here. Is a presentation copy, can it be downloaded? I'm not sure if you're asking about this this actual webinar. Yes, it is recorded and will be available for viewing after, if that's what you're asking. All right, last call. Any other questions? Anyone want to raise their hand? And Stu's wondering, can we get a copy of the PowerPoint deck? I guess your PowerPoint presentation.
It's about 12 megabytes, and I don't have a website of my own. I could send it to you, Ken, if you like.
Yeah, or we can talk with Dean and let's see about getting it posted. Okay, anyone else? Anyone raise their hand, ask a question? Okay,
yeah,
go ahead.
I'm sorry. The August 5th webinar was about 75 megabytes, as I recall, of as a WMV file. This one will probably be a bit larger, but
right.
It should be. It should help to have the voice in the background and be able to stop it at any particular slide you want.
Yeah, absolutely. Okay. Jim W6EB again. Go ahead.
Yes, one last question. Is the software by itself available for purchase?
You mean HFTA, Jim?
Yeah, the latest version, or is there any substantial difference from the version of, I guess,
Well,
5
the
or
one,
6 years ago?
oh yeah, there's very substantial difference. First of all, that was a DOS version that you've got if you had it from the 19th edition, and there have been many modes, many diffraction modes added since then that make it better. So either the 20th edition or the 21st edition, you'll need to get the antenna book, and then the program will be on the CD-ROM.
Okay, is there a substantial difference between the 20 and 21st?
You're going to ask the ex-editor of the antenna book that question?
Yes.
Yeah, there's substantial differences. Each edition is typically updated. About 20% of the book is updated. So
No, I didn't mean the book. I meant the HFTA.
oh no, between the 20th and the 21st, they're virtually identical.
Okay, that's what I was interested in. Thank you very much, Dean.
Okay, Jim.
All right. Let's see, one last one here. Ned, do you want to try your mic again? Go ahead, give it a shot. Okay, Ned, I'm not hearing you. One more time.
Well, let's try this time.
Okay, there you go. That worked. Did you
Okay.
do you have a question, or you just want to test it out?
I did want to test it out, and it's entirely operator error. I'm using a USB headset, and on the cord, there's a little dongle with a bunch of buttons, and I pressed one, and apparently when the light goes out, the mic is live. It's just the opposite of what I would think anyway.
Oh, you probably have the same type of headset I do. When the light's on, the set's muted.
Yeah. Can I ask? Is there a dollar cost for putting on one of these shows, and is it substantial?
There is a cost associated with it, but it's not anything that the club isn't able to pick up. So we're happy to do this. It's not a major thing for us.
Okay. A couple of years back, when Dean was leading NCCC, and I was doing the same for TCG. They sent out a DVD for SO2R.
Oh yeah.
And,
in fact, K6VVA was the guy that produced that.
Oh, okay. Thank you, Locust. Using that as an example, and these webinars, it's really great and helpful for us guys in the small clubs, because we don't have these kinds of resources.
Sure. No, we're glad to do that, and we will certainly take any suggestions for topics as well, and be happy to have the input. So, okay, we got a couple more questions. I'm going to grab these quick, and we'll wrap this thing up. Let's see. Can we get meaningful information using HFTA with simple antennas such as a dipole or a wire beam?
Oh yeah. As I said, the models of antennas used in the antenna book consist of dipole, 2-element Yagi, 3-element, 4-element, 5-element, 6-element, 8-element Yagi, where the biggest one, as I said, is an 80-foot boom on 20 meters. That should cover most cases.
Okay, I think I'll just take one quick look here yet, and let's okay, this is showing one more question, but for some reason, oh, here we go. What program did you use to view the file after using Make VOA?
What program did what?
What program did you use to view the file after using Make VOA?
Oh, after using just Notepad, I think. It's an ASCII it's an ASCII file, and that's the one that goes into to become an antenna file for VOA cap or VOA area.
Okay. All right.
If,
Well,
if anybody wants to know, it's a Model 11. It's a Model 11 style file for VOA cap. They can look that up in the VOA cap documentation.
okay, why don't you send the presentation roll back to me, and we'll wrap this up, and everyone can get out. And since I'm still on EY8 time, I feel like it's time to go to work, so I'm I'm ready to go. I got my
Okay, let's see. Change presenter, is that right?
Yep.
Back to Ken. And are you sure you want to make Ken the presenter? Yes. There you are.
All right, and I am going to go like that. Also, just bear with me 1 second here, folks. I want to unmute the rest of the staff too, in case they have any other comments. But anyways, big thanks to Dean once again. Excellent program. I know I played around with this a little bit once in a while, had questions, and this is fantastic because it just basically takes you through everything, and you can see it live how to do it. So Dean, thanks once again for all your work in this field and taking the time to demonstrate this for us.
You're welcome, Ken.
And reminder that our next event is October 16th at 2200 UTC. Dean had mentioned that he was doing some work with the LZ9W station, and Wally has agreed to give us a look at all the activity they've had going on this past summer, the antennas and towers and stuff they've been doing out there. I thought it was just be kind of a neat chance to get a look at a station for most of us in the U.S. here outside of the area and see what's going on in Bulgaria. So that registration link has been posted on contesting.com, QRZ.com, a few places. But if you need it, just drop me an email. I'll send you the registration link. And a reminder once again that we have recorded this event, and we'll get it posted, and we'll send out some notices as to where you can find the recorded event. So, Dean N6DE, anything else to add?
Nothing else other than thanks again, Ken and Dean and everyone for attending. This was a great job, Dean, and thank you, Ken, and to the PVRC for hosting.
You got it. Okay. Well, that's a wrap. Thanks everyone for attending, and we'll see you at the next one. So long.
Thank you, Ken and Dean.
All right. Bye-bye.